Welcome to the Electrical and Electronic Engineering Lecture Series. Your anchor person is Professor Michael C. Ndinechi. Our topic today is Modulation Part 1. Modulation means the systematic variations of the carrier wave, such as its amplitude, frequency, or phase, as a function of the message signal. Modulation may be continuous wave type or pulse type modulation. The message signal from the transducer, which is a time-varying current or voltage, is referred to as the information. To be relevant, the information signal must have some element of uncertainty associated with it so that when information transfer occurs, something new is gained. This element of uncertainty is the reason for the statistical treatment of information in communication theory. Modulation of a sinusoidal wave. Consider a typical sinusoid given by V of t equals a cos omega t plus phi, where Vt equals the instantaneous value of voltage, A is the maximum amplitude, omega is the angular velocity in radians per second, and phi is the phase angle in radians. If any one of these three parameters is varied in accordance with another signal, normally of a lower frequency, then the process is called modulation, and the first is said to be modulated by the second. When modulation is performed on the sinusoid, one of the parameters of the Vt is varied in sympathy with the modulating signal Vm of t. Allowing Vt to have time-varying parameters, then equation 1 becomes V of t equals A of t cos phi t, where phi t is equal to 2 pi ft plus phi. Equation 2 has a phasor representation which consists of a rotating member of length at making an angle theta t with the abscissa. Since theta t is equal to 2 pi ft plus phi, it then follows that the theta dt is equal to 2 pi f. Therefore, the theta dt times 1 over 2 pi is equal to f, equation 3, and this is a time-varying frequency referred to as the instantaneous frequency of the wave, Vt. This gives a general sinusoid with time-varying parameters as Vt equals A of t cos 2 pi ft plus phi t. We call that equation 4. Therefore, three basic classes of modulation can be isolated from equation 4 as shown in table 1. For the condition where A of t is equal to kVm of t, we have what we call product modulation, and the case is referred to as envelope modulation. Likewise, phi of t equal constant, we have what we call conventional amplitude modulation. Now, if A of t is equal to constant and phi of t is equal to k into Vm of t, we have what we call frequency modulation or frequency modulation with pre-emphasis, and the case is referred to as angle modulation. The third case, which is the composite modulation, is where the condition A of t equals k Vm of t and phi of t is also equal to k Vm of t. When that happens, we have single sideband, asymmetrical sideband, independent sideband, vestigial sideband, compatible single sideband, and single sideband FM. Purpose for modulation. The need to modulate arises from a number of reasons. 1. To relocate baseband information so that it is spectrally adjacent to the high-frequency carrier. This frequency translation makes electromagnetic propagation much easier. Both transmission power and antenna size may be reduced as the carrier frequency is increased. 2. To provide a capability of frequency division multiplexing many baseband signals. And 3. To increase the transmitted signal redundancy, thereby gaining a measure of immunity to the signal corruption introduced by the channel. 4. To ease the radiation process. 5. To allow multiplexing many signals in one channel. 6. To assign channels of frequencies. 7. To reduce noise and interference. 8. To avoid equipment limitation. And 9. To match the signal to the transmission channel. Now, amplitude modulation. Amplitude modulation is defined as a system of modulation in which the amplitude of the carrier is made proportional to the instantaneous amplitude of the modulating voltage. If the carrier voltage and the modulating voltage be represented by Vc equals AC sine omega Ct and Vm equals AM sine omega mt respectively. Note, the phase angle has been ignored since it is unchanged by the amplitude. When the carrier is amplitude modulated, the proportionality constant is made equal to unity and the instantaneous modulating voltage variations are superimposed onto the carrier amplitude. When there is temporarily no modulation, the amplitude of the carrier is equal to its unmodulated value. When modulation is present, the amplitude of the carrier is varied by its instantaneous value as shown in Fig. 1. Distortion occurs if AM is greater than AC, and the ratio AM over AC is known as the modulation index, M. The value of the modulation index lies between 0 and 1 for optimum operation. Look at Fig. 1, you see AC, the amplitude of the carrier, being modulated by the amplitude of the modulating signal AM. Then the output is given as V0. So from Fig. 1, we can write that V0 is equal to AC plus AM sine omega mt. But remember that AM is equal to MAC. Then V0 will be equal to AC plus MAC sine omega mt. If we simplify further, we have that V0 is equal to AC into 1 plus M sine omega mt. Call that equation 5. The instantaneous voltage of the resulting AM, therefore, is given as V instantaneous equal to V0 sine theta, which is equal to V0 sine omega Ct. If you simplify, substitute the value of V0 from equation 5, you have that instantaneous voltage will be AC into 1 plus M sine omega mt times sine omega Ct, called equation 6. Expanding equation 6 using trigonometrical relation, in the case of sine x sine y, will give you half cos x minus y minus cos x plus y. And that yields that equation 6 will become V instantaneous equals AC sine omega CT plus half MAC cos omega C minus M omega MT minus half MAC cos omega C plus omega MT, equation 7. Now, if we substitute omega with 2 pi f, we have equation 8. Now, equation 8 represents the AM wave. And if you put that equation 8 into a spectrum analyzer, it will yield Fig 2. And that Fig 2, you will now see that FC is at the center, and FC plus FM is to the right, and FC minus FM on the left. So the spectrum analyzer will give this plot. Now, comment. It can be seen from equation 8 that the amplitude modulation wave contains 3 terms. 1. The first term, FC, which represents the unmodulated carrier frequency. 2. 2 additional terms produced as sidebands at FC minus FM and FC plus FM. The frequency FC minus FM is termed the lower sideband LSB, and that of FC plus FM is termed the upper sideband, the USB. The bandwidth required for AM is twice the frequency of the modulating signal. The carrier, which carries no information, is also transmitted. The baseband signal, which extends from FM from 0 when modulated, covers a frequency range of 2 FM. One of the sidebands is actually redundant since it carries exactly the same information as the other. Consequently, it is possible to eliminate one of the sidebands without affecting the transmitted signal. Since the carrier carries no information, it can either be suppressed or eliminated. When the carrier and one sideband are suppressed, the signal is referred to as single sideband suppressed carrier, SSB-SC. When only the carrier has been eliminated with the 2 sidebands present, the signal is referred to as the double sideband suppressed carrier, DSB-SC. The appearance of the AM wave is as shown in Fig 3 for 1 cycle of the modulating sine wave as derived from Fig 1. It is called the envelope of the AM wave, given by the relation V0 equal to AC plus AM sine omega t. Note, the envelope of the modulated wave will have the shape of the modulating signal Fm of t, provided F0 is far greater than Fm and m is less than 1. When m is equal to 1, we have 100% modulation, and the modulated amplitude varies from 0 to 2A0. When m is greater than 1, we have overmodulation, and there is envelope distortion. Recovery of such signal with envelope distortion required a coherent or synchronous demodulation scheme. Thank you for listening. Please like, share, and subscribe. Drop your comments, questions, or topic you want me to lecture on the comment section so that part 2 of this modulation will come to you. Thank you.